Hi, my name is Alekseishindin. I'm Associate Professor at Radiophysics Department of Lobachevsky University in Nizhny Novgorod, Russia. In this video, I present the report Response of 630 nanometers optical emission on ionosphere heating by powerful radio wave. This report is about numerical modeling of ionospheric heating by powerful HF radio waves influence on the nighttime air glow and comparison of the results with experimental data obtained at the Sura heating facility. We model the effect of suppression of the background air glow during the heating as well as its recovery and so-called afterglow after the heating switching off. Results obtained allow to estimate the increase of electron temperature and rates of some photochemical reactions in the heated ionosphere. It is known that optical emission of atomic oxygen, state O1d, 630 nanometers red line of the ionosphere modified by powerful HF radio waves exhibits two opposite effects. The first one is the enhancement of the emission intensity, artificial optical emission or artificial aurora, due to increasing collisional excitation of O1d caused by electron acceleration by parametrically excitation plasma waves. The second effect is the suppression of the background emission due to slowing down of the dissociative recombination of O2 with increasing electron temperature. Here, alpha is the recombination coefficient. The main purpose of the work is numerical simulation of the second effect, namely the dynamics of the ionosphere red line emission. 630 nanometers transition O1d O3P2 caused by powerful radio wave switching on and off, and comparing the simulation results with experimental data obtained at the Sura heating facility. Figures 1 to 4 display experimental results of studying influence of powerful HF radio waves on the red line optical emission of the ionosphere obtained at the Sura facility on September 14, 2012. Sura facility radiated vertically at the frequency 5.33 MHz with the schedule 150 seconds on and 270 seconds off. The effective radiated power was about 200 megawatts. The night sky images presented in figures 1 and 3 were obtained with CCD camera with 20.6 degrees field of view. Figure 1 presents the image obtained at 22 hours 9 minutes local summer time. That corresponds 18 hours 9 minutes UTC. The heating session started at 18 hours 7 minutes UTC. It is well seen a noticeable enhancement of the emission brightness. The maximum brightness achieved 50 relays. Figure 2 shows the brightness dynamics. Point T equal 60 seconds corresponds to the pump wave switching on, and point T equal 210 seconds to the pump wave switching off. At the point with maximum brightness across the camera field of view shown by a red cross in the figure 1, it is seen that in about 25 seconds after heating switch off, the decay of the air glow brightness slows down. In some sessions, even an increase in brightness is observed in this time. We call this afterglow. Figures 3 and 4 illustrate the opposite effect of suppression background emission recorded in the next heating session at 18 hours 13 minutes UTC. In this session, performed at the pump wave frequency 53-30 kHz, the suppression reached 10 relays already in about 50 seconds after pump wave switching on. Then the emission intensity starts to recover. The recovery continues after heating switching off till time 310-320 seconds and then slowly decays. During time between 240-420 seconds, the air glow brightness exceeds the stationary background level without heating, afterglow. We try to model the latter effect, namely the suppression of the background due to ionosphere heating and successive afterglow. The next slides describe theoretical model. The red line air glow measured in the experiment is determined as an integral over the entire range of heights where excited atoms O1d exists. Here A6300 is Einstein coefficient, O1d is the concentration of excited atoms. The brightness value is measured in relays. Under natural conditions, in the absence of the HF heating, the maximum of O1d concentration is about 1200 centimeters in -3 degrees, is reached at altitudes 230–250 kilometers. At these altitudes, excited atoms in the O1d state appear as a result of the sequence of charge exchange reaction and dissociative recombination of electrons with molecular oxygen ions. O, O2, O+, O2+ are atomic and molecular oxygen and the corresponding ions. The system of differential equations describing the dynamics of O2+ concentration and O1d concentration under these reactions with account of the electron heating presented here. Here, K1 is the rate coefficient of the charge exchange reaction. Alpha is the coefficient of dissociative recombination. TO is electron temperature at the powerful wave turning on, beginning of heating. Ne is the electron concentration, eta is the probability coefficient, tau F is the effective lifetime of the atom in the state O1d. For calculations, we use the value of the effective electron lifetime at the O1d level, Tf, different from the radiation lifetime, Tr, 107 seconds. In calculating tau F, the decrease in the concentration of the excited atoms in the O1d state as a result of deactivation in collisions with nitrogen and oxygen molecules N2O2 is taken into account. According to the Lincoln-Cogger, under ionospheric conditions at the studied altitudes, tau F is about 35 seconds. Equation 6 is the electron thermal conductivity equation with the source Qt, situated near ZO, the upper hybrid resonance height of powerful radio wave related to the electron heating by the pump electromagnetic wave and parametrically excited plasma waves. At this slide, you can see used expression for Qt. The initial condition for equation 6 is Te is equal to To. H on Z is the Heaviside function. Z is the height. ZO, the upper hybrid resonance height, is the height of the center of the heating source. Delta Z is equal 1 km is the characteristic width of the heating source. T on and T off are the times of turning on and off the powerful wave, respectively. dt is the coefficient of thermal conductivity. Le is the mean free path. Delta is a fraction of energy lost by the electron during collision with heavy particle. Me is the mass of the electron. Nu E is the electron collision frequency. EO square is the intensity of the pump wave electric field. For calculations, we use for EO the underlined empirical expression, where VO is equal 175 kilowatts is the power of the transmitter pumping the ionosphere. Epsilon is much more than 1 is the coefficient enlarging the source due to inclusion of plasma waves in heating process. Based on the solution of equations 4, 6, the height distribution of concentrations O2 and O taken from the empirical model of the ionosphere NRL MSISE and the electron concentration profile NE taken from the International Reference Ionosphere Model IRI and modified taking into account the conditions of the experiment a behavior of the concentration O1d and the brightness of the optical glow in the ionospheric experiments performed at the Sura facility was modeled. Examples of the simulation results are shown in figures 5 and 6, blue lines. Figure 5 displays the distribution of O1d concentration for the heating source position ZO is equal to 270 km after subtraction of the background. Figure 6 exhibits the emission brightness dynamics on the ground for two different sets of the simulation parameters, the same as in figure 5, dashed line and solid line slightly varied for better coincidence with experimental data, red dots taken from the figure 4. A suppression of the 630 nanometers optical emission was observed in the experiments at the Sura facility in 2010-2016 in the number of sessions with heating of the ionosphere by powerful electromagnetic wave of ordinary polarization. Previously, similar but weaker effect was observed at Platteville and Arecibo facilities with heating by extraordinarily polarized powerful wave. For ordinary polarization, this effect was most probably masked by the opposite one, an increase of the emission brightness caused by oxygen atoms collisions with electrons accelerated by parametrically excited plasma waves. The effect caused by ordinary pump wave is stronger than for extraordinary one and is accompanied with an increase of the emission intensity after turning off the heating, afterglow. Using the theoretical model, which includes the equations for charge, exchange reaction, dissociative recombination, and electron thermal conductivity, we try to combine the simulation results with the experimental data. From figures 5 and 6, it is seen that temporal behavior of the measured emission brightness is qualitatively similar to one obtained from simulations. The suppression of the emission density is determined, as already mentioned, by a decrease in the coefficient of the dissociative recombination alpha with increasing electron temperature, a decrease in O1d concentration in accordance with the equation 5, and consequently the brightness of optical emission B. When the pulse wave is turned off, the electrons cool down, Te decreases, alpha and therefore O1d concentration increase, which leads to a temporary increase in brightness, afterglow. The characteristic times of brightness variations during simulation is determined by the reaction coefficients and, as we see, are close to the experimentally observed ones. With some perhaps arbitrary variation of simulation parameters, it is possible practically to combine the theoretical curve with the experimental points. Variations of parameters are given in the captions to the figures 5 and 6. Notice that for the long heating, the stationary brightness value equal to the initial one should be achieved. The same brightness should be attained after the heating switching off and temporary brightness increase, afterglow. Thus, modeling the effect of electron heating on the behavior of the glow in the 630 nanometer line may be useful for estimating a number of ionosphere parameters. In particular, there are a concentration of excited oxygen atoms and its variations during and after heating, the height of the glow source in the red line, the magnitude of the electron temperature increase under heating, the reaction coefficients responsible for the brightness dynamics. At the same time, it remains unclear why in some successive heating sessions, very close in time, an abrupt change in the observed effect can happen. A brightness grows in a compact spot with its suppression in the sufficiently wide region is replaced by heating sessions when the electron acceleration does not exist or is very weak, and the suppression of the air glow prevails and is observed. In these references, it was shown that the suppression effects occurred when the pulse wave frequency approaches the critical frequency of the ionosphere as a result of the after-sunset drop of the ionosphere. Apparently, in the experiment presented in this work, there was a short term with one session approaching of the pulse wave frequency to the fourth electron gyroharmonic due to altitude variations of the ionosphere. That's all. Thank you for attention.